Okay, what you have, what you can see now is an impeller with a splitter. The splitter is this small blade in the center of these two main blades. We're going to use a MillTurn machine. Generally, impellers are done on 5-axis milling, but we're just changing it and moving on to a 9-axis MillTurn machine. To show you how the machine looks like, I'm going to open the machine. You open the machine simulation. Okay, this is how our machine today looks like. It's a Morisaki NTX 2000. It has got two spindles, a main spindle and a sub spindle. It has got a B-axis, that's a head. It's basically going to rotate around, swivel around Y-axis. And then we have a lower turret which has both X and Z axis. So it's about 9 axes that we have in this machine. Plus the sub spindle can go in the front, ahead in Z axis, and can grab the component and come back, and then we can start the machining again. So we're going to use this machine to cut our impeller today. All right. Let me close. So before the webinar began, what I did was I created a couple of steps which generally take some time on a MillTurn machine for such a part, and that is to create the target envelope, basically the envelope for turning. Now SolidCAM has this facility that the moment I give this impeller to a MillTurn machine, it automatically creates an envelope for turning. Makes the turning operations much more simpler. You don't have to create any additional geometry for it. And then we have our stock geometry, which is nothing but a cylinder. This of course can be edited by the user. So if I double click this and I put the dimensions, this is about 125.728. That's basically the radius. So we are going to have double of that, about 250 as our diameter, and also the length of about 154. Now I have taken this length in such a way that it fits my stock geometry. The fixture geometry. So what is my fixture? My fixture looks something like this. I'm going to hold this on a fixture onto the main spindle. So I have got the holding fixture attached to my impeller. So the stock is being held on this holding fixture, and the holding fixture is then held onto the main spindle. Right. So since my stock is a cylinder and not and it's not something that's already having some shape, we need to do the turning of this particular cylinder. So let's start first with the facing operation, and then we are going to do some rough turning. We'll finish the blank and then start the 5-axis operation. So this is going to be our agenda today for today's webinar. So let me add turning operation, facing. Now even before we start this, what I'm going to do is I'm going to switch on my geometry, not the stock but the target geometry. It's got a lot of points because of the arcs that it has generated. So let's add a facing operation. So what do we have in the facing operation? First of all, because we are using a multitasking machine, we need to specify on which sub-machine does this operation happen. So this operation can happen actually on 4 sub-machines. It could happen with a combination of the upper turret, or basically the upper head and the main spindle, or lower turret and the main spindle, or upper turret and the back spindle, or the lower turret and the back spindle. So I need to tell to SolidCAM on which sub-machine this operation is happening. Obviously, we're going to do this on upper turret and the main spindle. And I already have some geometries out here. I'm going to pick contour, and this geometry is what I have selected. A simple straight line which has been generated already by SolidCAM. And we're going to have about 5 millimeters of stock to be removed in facing. Okay, now I can see that the geometry is starting from this point out here and it ends up to here, but actually my my stock is all up to there, from there to the center. So what I need to do simply is to go to modify geometry. You can see that it's already extended this geometry up to the end point of the stock. I only need to now push that geometry down to the center. So I will use the auto extend to stock. So it is now extended that curve down up to the center, which gives us a nice face to do our facing. On the tool, I'm going to select, I already have a tool. I'm going to use a DNMG insert, and this DNMG insert is going to be held in an adapter or holder that's going to be mounted on my main spindle. This is how my adapter looks like, or the holder looks like, and this holder is going to be mounted on the main spindle. Now, starting with 2014 version of SolidCAM, these holders are going to be a standard part of our holder library. These are all going to be available to us in the holder library. So you can choose from the holder library and then start using it. So this is how my insert and the holder looks like. I've got a clamping device on the insert, and that's my origin of the turning insert. Okay, let's select this tool. Now, I don't want this tool to be straight. Why I don't want it to be straight is because I'm also going to use this for my turning. So what I'm going to do is, I would like to tilt this tool at about 15 degrees so that it gives me enough reach when I'm doing turning. So what I simply have to do is put in a value of minus 15 degree. You can see what's happening out here. The tool has tilted itself. I can look at the feedback that it gives me. I'm getting a nice feedback here saying that the tool has tilted. If I put plus 15, it would have gone on the other side. So it gives me a feedback. So I'm going to put minus 15 degrees here, so that my head is now going to tilt 15 degrees and do the facing operation. Safety values, I'm going to give about 35 millimeter on the X and 50 millimeter on the Z. That's where my safe position lies. In the technology, of course, I don't want any offset on Z. I just want that to be cleaned up. And I'm going to use 1 millimeter as my step over, and it's going to be a one-way machining. All right. In the link, I want the approach and retract to go to the right safety corner, and the right safety corner is defined by these two values out here, the 35 and 50. Right. So let's hit save and calculate. The calculation is already done. If I look at my HostCAD simulation, I can see the toolpath very nicely. Now, simulation here can be of three types. So we'll see the first simulation, and that's the turning simulation itself. It's a simple 2D XZ view in which I can look at the turning simulation. Let me go step by step. Now, the disadvantage, you could say, in turning sim, just the plain turning simulation, is that I can't see the holder, but you can see the entire operation. You can see that, and then it goes back to the safe position. So the first type of simulation is the turning simulation. The second type is the solid verify simulation, where you can see the fixture, you can see the stock, and also you can go step by step. I can see the holder here. This comes with the holder, so I can have a look at how the simulation is happening. That's it. Another simulation obviously is going to be the machine simulation itself. So I have got a third type of simulation, and that's the machine simulation. It becomes much more clear on how my machine simulation will look like. So I'm going to increase the area of my simulation. you can see on the main spindle we have mounted the fixture. On the fixture we have mounted the stock, and I have the head with my tool and the holder. And now let's decrease the speed a bit and run the simulation. Right. So you can see that my facing operation is now complete. Right. And this is inside machine simulation itself. So it gives you a clear-cut idea on how it's going to work or function on our machine itself. Right. So we are done with our facing. And now I would like to do the rough turning. I'm going to use a different technique here for my rough turning. Since I have got the lower turret, I'm going to use what we call as a balanced rough, wherein I do the roughing simultaneously with both of my turrets, the upper turret as well as the lower turret. It gives me a big advantage. There are two main advantages to this. First advantage is that the material removal becomes double. The speed of material removal is just doubled because you have two depth of cuts being taken at the same time. The other main important thing is our cutting is more balanced in the sense that we have got forces acting on from both the sides, so the cutting becomes much more stable. Right, so let's now run the roughing. Let me add from the turning operation balanced rough. We have the, so here in balanced rough I have got the master machine, the sub machine, and the slave sub machine. My master sub machine is the upper turret and the main spindle, and my slave sub machine is the lower turret and the main spindle. Also I have got contour selected here. If I have to show you the contour, it's this pink colored contour that's being shown up. Starts all the way from this chamfer and ends all the way up to this point. Okay. Now because we have got the contour derived from a geometrical operation, I'm going to extend again this to the stock. If it is left out even few microns, it will extend the contour to the stock. The next important thing is to define the tool that is going to be used for my master submachine and the slave submachine. So on my master, I'm going to use the same tool that I used for my facing. So I'll use the external turning DNMG insert along with the holder, and I'll provide the same 15-degree tilt to this particular tool. Over here I have got the orientations on which I can pick and place the tool. I've used this as my orientation with a 15-degree tilt. The slave tool, I'm going to use a different insert. I'm using a TNMG insert here along with my shank, and my mounting is in this way. Select this. So I have got my tool here, and this is the orientation that I have chosen. Levels, again my custom safety distance 35, and distance in Z is 50. Technology, I'm not going to use a simultaneous method, but I'm going to use a trailing method. We have got two methods out here, simultaneous as well as trailing. I'm going to use a trailing, and the distance I'm going to maintain is about 1 millimeter between the slave and the master tool, so that the master tool always is in the front, the slave is trailing behind by 1 millimeter behind the master tool. Roughing, I'm going to keep about 0.6 millimeter on the X direction and 0.2 millimeter material on the Z direction. Step over of 2 millimeter, that means 2 from the master side, 2 from the slave side. So in effect, we are taking about 4 millimeters at one go. Strategies, I'm going to use a non-descending motion. I don't want to dig into the material to cut it. I'm not going to break any edges because I don't need to break any edges here. Link, approach and retract to the right safety corner. Right, so let's hit save and calculate. Calculation is done. Now again, we can look at the simulation in all three modes. Let's go to the turning simulation. You can see that the stock has already been updated from the facing, and we can start the simulation here. You can see both the tools approaching. The first tool is already near the job, and the second tool is 1 millimeter away, the slave tool. You can see that 2 millimeters from top, 2 millimeters from bottom. At a time, we are taking about 4 millimeters. So this increases the speed of cutting, also the material removal. That's it. So we have done the turning using balanced turning. We can also see the same thing in the solid verify. Quickly reduce the speed. Start. Okay, we can quickly jump to the machine simulation because that's going to be very interesting. I'm going to go to the front view of this machine and zoom and run it. So we have the master tool tilted at 15 degrees, and then we have the slave mounted on the bottom turret. Okay, let's start. Okay, perfect. So we have done the turning. All I now need to do is to finish this blank so that it's now ready for my 5-axis operation. Right, so what we are going to do now is I'm going to add turning operation. It's again going to be contour 1. I'm going to select the same tool that we used for roughing, maybe change the insert or something. Okay, minus 15. Levels, again custom safety, put it at by the way, this custom safety distance could be put in your setup so that you don't have to enter it every now and then. Technology, we are going to use finish only, and the entire geometry will be cut. Non-descending motions. Let's save and calculate. Simulate. Let's run the solid verify. So we have the roughed out stock, and we can now run the finished cut. That's it. Single cut, and it's all done. So we have now finished the turning. We saw facing, balance rough, and the turning itself. Now before we begin the 5-axis part, I would like to show you something, because this is again very important in SolidCAM. If we look at the operation, I just did the finishing. I've finished, but my turret still, the lower turret still remains at the home position. Now this can be dangerous when I'm trying to do a 5-axis operation. If the upper head is going to tilt almost to 90 or beyond 90 degrees, then there's a possibility that the head might touch somewhere either on the tool or on the turret itself. So I need to move the turret back to a safe position. How do I do that? I can do that very easily. First, let me switch off the sketches, because yes, now it's pretty clean. We have got something called as a machine control operation. So I'm going to add a machine control operation to the lower turret. So I have got all my sub machines out here. I'm going to add the lower turret. The first thing that I want to do is to unload the tool. That means rotate the actual tool to some other position so that I don't have any tool on the cutting side. So I'm first going to unload the tool, and you can see that the station 1 is the only station that is occupied on the lower turret. There are 9 other stations that are still empty. I'll go to station 6, which is empty. So I'm going to move the turret to station number 6, which is empty. And then I'm going to add a movement in Z, 300 millimeter, but not using the part home, but using the machine home. So clicking on the home, I get either the part home or the machine home. And I can get the preview out here. This was where my home is. I've moved further 300 millimeters. All right, let's save and run the simulation. Machine simulation. Right, so this is where my position was before we ran the machine control operation. So if I go step by step, you'll see what is going to happen. My tool first is going to be unloaded. You can see the tool rotating station by station. So my tool has now gone somewhere below. So it's in a safe position. I don't have any tools up here. What is the next step? It's gone to the safe position. I have moved it back 300 millimeters from its home position. So it's in a safe position, which will allow my upper head to function properly. It can tilt, it can rotate without the possibility of it touching or crashing into the lower turret. Now you could move the lower turret to 2 positions. You could either take it to the extreme right near the sub spindle, or you could take it under the main spindle itself. So it depends on where you want to move it. I have moved it under the near the sub spindle. Okay. So we have done our machine control operation. I'm going to exit from this. You can see that the machine control operation also becomes a part of your Toolpath 3. Let's now start with our 5-axis operations. We are now going to do a roughing of this particular area between these 2 blades, including the splitter. In SolidCAM, since 2013, we introduced this new functionality called Multiblade Machining. Multiblade Machining is meant for parts like this that is being displayed. It could have a splitter, or it could have more than one splitter, so it doesn't matter. What I need to do is simply add milling operation, and you have this multi-blade machining. Pick the multi-blade machining. Again, the sub-machine is being asked. Again, the part is still on the main spindle, so it's going to be the upper turret and the main spindle, so that's the sub-machine. Geometry, I already have some defined geometries, so what I'm going to do is I'm going to pick those defined geometries. The first thing that I'm going to do is to change the strategy from offset from hub to offset between hub and shroud. Okay. Blades, splitter, and fillets, that's what I need to pick. So I'll pick the geometry that has been already saved as blades. If I click on show, this is the geometry that was defined as blades. 2 main blades and the splitter, including the bottom fillets that we need to pick. The hub surface, I'll pick the hub surface, and if I click on show, the hub surface is somewhere here. It doesn't matter if your hub surface is near the blades or not. It just needs to know where the hub surface is, or how the hub surface is. Internally, it's going to revolve and create another hub surface. And then I have the shroud, which is the upper part of the blade. If I click on show, it's the simple small surface that's there on the upper side of the blade. That's my shroud geometry. I'm going to keep a stock of about 0.35 on the blades for finishing and about 0.3 for the floor to finish. I don't need to keep any offset on the shroud part. The tool I'm going to use is a taper ball nose. I'm going to use a diameter 12 with tip diameter about 6 millimeter, that is R3, and a taper angle of about 3 degrees. So it's a taper tool. I'm going to select that. Levels is automatic. I don't need to specify anything here. I just simply need to pick the auto detect dimension and position. Toolpath parameters, everything almost is automatic. So what we are going to do is 10 layers and 10 slices. That means 10 depth of cuts and 10 cuts in between these blades is what we are going to be putting in as parameters. In the area, I'm going to start at about 5% from the top. I'm exactly not going to start at 0 because sometimes you have this edge issue. So I'm going to start 5% of the geometry below, and I'm going to end at 100%. That's not an issue. Sorting, it's going to be a zigzag starting from the leading edge, and we're going to order the slices or cuts from left to the right and anything in between. Tool axis control, again everything is default, works fine. Link is automatic. You can see the function has been written specifically for such geometries where the user is not required to input many parameters. Gouge check, I don't need anything. Roughing and more, what I simply need to do is to rotate the cuts. Now because I have got one, there are totally 7 segments on the blade, on the impeller, so I'm going to put number of segments as 7, and I need to machine all of them. Machine control, I don't need to define anything. Miscellaneous parameters, also nothing. I'm going to save this, exit, and calculate this toolpath. It's going to take about a couple of minutes. You'll have to bear with me till then. Okay, it's almost done the calculation. Now it's generating the preview of the toolpath. It should take another few seconds. Okay, that's done. Now, if you look at the toolpath itself, now this is one of the important features now that has got improved vastly over the last version, and that is the display of the toolpath. So I select it, and you can look at the toolpath. You simply have to pick the geometries, the hub, and that's it, and it generates a nice clean toolpath. Okay, what we are now going to do is we'll just run the simulation quickly to some extent, not the complete simulation, because that complete simulation will take some time. Again, you can look, the stock is updated to the last turning. I'm going to switch off the holder and run the simulation. Okay, let's stop this and also look at how the machine simulation would look like. This will take about another 10-15 seconds because it needs to load the entire toolpath, which itself is huge. All right. Let's look at how the machining now look like. Let's increase the speed a bit so that I can show you the result. Okay, it's finished one blade, so I'm going to rotate it in and show you the result. So it's completed one segment and it's going to the next segment. So on, it will finish the other 7 segments. All right. Now that we have done with the roughing, what we're going to do now is run the finishing of the main blade. So let's add multi-blade, blade finishing. And I'm going to use the main blade as the geometry. If I show you what the geometry looks like, it's only the single blade that I've picked, including the fillets at the bottom. Okay, the hub surface remains as hub. Of course, the strategy is going to be between hub and shroud. Shroud tool, we're going to pick the same tool for finishing. Levels is automatic, and technologies, I'm going to put maximum downstep of 1 millimeter. We're going to cut the entire area full, and we'll start at about 5%, and we will not go 100%, but we'll end at about 90%, because as you can see on the fillet is like a variable fillet, and I don't want it to cut the fillet during finishing the blade. We will cut the fillet separately. In the sorting, I'm going to have spiral starting from the leading edge, so it's going to be like a spring wound on the blade. Tool axis control is automatic. Link is automatic. I don't need any gouge check because the gouge check is already built in. If any special gouge check requirements are there, then I need to specify the gouge check. Okay, let's save this and let's run the calculation of this. take another 20 seconds or so to finish the calculation. Calculation's done, and this is how my toolpath would look like. Neat, starting all the way from top, spiraling down to the bottom. I could further go down if need arises, but this is how my toolpath would look like, clean and without any issues. Right. Now that we have done the blade finishing, we can also do the blade finishing of the splitter in the same way. There's another very interesting thing that we need to do is to finish the fillets at the bottom. Question? The question somebody asked is, what is the tolerance that you could expect on the final product? Now, the toolpath tolerance altogether out here is set at 10 microns. So the toolpath is going to be plus minus 10 microns. And obviously there are tolerances on the machine, the tolerances for holding, the tolerance for the tool. My experience is about 30 to 35 microns is the end result tolerance that you would get if you use 10 microns as a tolerance inside the toolpath. You could further tighten it inside the toolpath. You could bring it down to 2 microns or even 1 micron, but actually that's not going to help much because it finally also depends on several other factors like your holding, the tool, the machine repeatability itself. So there are many factors that join in together. So safely you could assume about 35 microns as your final product tolerance. I hope that answers the question. Right, so what we are now going to do add is another multi-blade operation, and this is for fillet. I'm going to pick again the main blade because I just want to finish the fillets of the main blade and the hub. Okay, let's pick the tool. I have a different tool this time. I'm going to pick a tool with a smaller tip radius because I need to finish the fillet. Okay, levels is automatic. Toolpath, technology, I'm going to have 6 cuts from the blade side and 6 coming from the hub side, and we are going to use a side step of about 0.3 millimeters between the passes, and it's going to be one way starting from the leading edge. There's going to be an improvement in this in the next release of SolidCAM. Instead of one way, we are going to have spiraling of the toolpath. Instead of just going one way, lifting up and then coming down again, we will spiral even for the fillet. Okay, so tool axis control is again default. Link is automatic, no gouge check needed. I'm going to save this and calculate. It's going to take again a minute or so we'll have to bear the time. Okay, it's done. Let's look at the result, and this is how the fillet finishing would look like. It's going to go all around the fillet, and it's going to finish the fillet, only the fillets. It won't touch the blade, neither it will touch the hub. Of course, it will just lightly finish the hub also, because we have taken 6 cuts coming from the hub side and 6 cuts coming from the blade side. So it's going to finish the fillet. Now what remains to be done is to run the hub finishing. So we will use again the multi-blade operation, hub finishing, blades, that's the geometry. So it's going to finish the area in between those blades, and the hub geometry is selected out here. Tool, I'm going to use the same tool that I used for fillet finishing, because I would like also to lightly touch on the fillet side. Toolpath parameters, technology, we're going to take 1 millimeter as our side step. Sorting, I'm going to do zigzag starting from the leading edge, go left to right. Tool axis control is default, works fine. Linking is automatic. Let's save and calculate this toolpath. Okay, that's also done. Let's see how the toolpath looks like. You can see that the floor has been completely done using a similar strategy like roughing, but it's only doing the floor finishing. Of course, I can rotate this to encompass the entire impeller. Now, if I take an output from this, for example, if I take an output from the fillet finishing and generate a G-code, okay, you can see that I get 2 outputs. Why do I get 2 outputs? Because this machine has got 2 sub-machines, the main upper turret and the lower turret. So one of the programs, 1.nc, goes to the upper turret, and 2.nc goes to the lower turret. And you can actually run both of these simultaneously. So if you can see, in the lower turret, we actually don't have any program when we just output the fillet, because the fillet doesn't get machined from the lower turret. It gets machined only from the upper turret. Supports G43.4, which is the RTCP on Fanuc 31i, and this is the 5-axis program. But if I take an output now of the balanced rough, where we are using both the upper and lower turret, we're going to get a different kind of a result, but we're going to still get 2 files. I have 1.nc and then I have got 2.nc, and you can see that one starts, there is the waiting code M102, and you have got M102 waiting code out here, and then M103, another M103. So you have got waiting codes coming up here. As and when the machining starts, you have got the waiting codes coming on either side. So this is how this part will be machined on a complex MillTurn machine like Morisaiki NTX 2000, where we saw both turning operations, machine control, moving axis to safe positions before we start the next operation, and also the impeller functions inside SolidCAM, the multi-blade functions like roughing, finishing of the blades, fillet finishing, and the hub finishing itself. If there are any questions, I'm open for questions. If there are no questions, then